All right. Yeah, welcome everyone to today's session of the InfoSec Research Seminar here at UCL. It's my great pleasure to welcome Giovanni Cherubin from the Alan Turing Institute. He's working there as a research fellow, and he's looking into machine learning and privacy problems. And today he will tell us more about his latest research on black box leakage estimation. So Giovanni, it's great to have you here. Take it away.
Oh, thank you, Philip. And thank you. Good afternoon, everyone. And thank you for having me here. It's great pleasure. Right. So today I would like to tell you about some advances in black box leakage estimation. And that is, we'll be interested in measuring how much, private information some system is revealing to some attacker. And by system, what we really mean is something generic. We could be interested in the information leakage of a computer program, of a machine learning model, or even some hardware, as you'll see. Now, the turning point of this talk, if you wish, is that this very problem of leakage estimation can be seen as a sort of equivalent to the problem of supervised learning, as in machine learning. And this sort of equivalence will enable us to use many tools from the learning theory and many practical tools for estimating the leakage on real-world systems. So, I'll take my headphones. I have right. So, I'm sure there's no need to convince you that many security and privacy breaches nowadays depend on information leakage. And one of the perhaps best known cases was the case of the Netflix prize. The Netflix prize, Netflix at some point decided to share customers' data, which they anonymized somehow. But then two researchers immediately after realized that just by using some auxiliary data, which was also publicly available, they were able to reconstruct some of the customers' data and essentially to de-anonymize customers. And of course, this was source of great embarrassment, and I believe also a lawsuit. But of course, information leakage issues didn't stop there. Very recently, Carlini shared a very nice blog post where he showed that a language model, GPT-2, might leak information and private information that was used for training the model itself. So in this particular case, you see the private addresses and email addresses of a company. But of course, information leakage doesn't stop there. One of the most discussed areas for information leakage and application areas are anonymity networks. And there are several attacks against the Tor network, for example, which exploit little information leaks in order to either de-anonymize users or to predict what the users are doing. And finally, for completeness, I'd like to remark that information leakage, of course, is not just a problem of privacy. It is also a problem for security. And one example was the Spectre attack, where researchers were able to exploit a timing side channel, and therefore this sort of leakage coming from the side channel to reconstruct data sitting on a PC. So how can we do leakage estimation, and what does it mean to do it? I'm going to start with a very simple example. The idea is that we model our system as a sort of black box, as a sort of a channel, which we have to define the secreted pieces of information that we're interested in protecting. And we have to define what are the quantities that can be observed by an attacker. So let's stick to this very simple example of a computer program. Now this program takes as input some secret value, and it returns, if the secret value is a multiple of 8, then it returns the secret value itself. Otherwise, it returns some garbage output. Now, the question in leakage estimation is exactly, is this function or is this computer program secure? And you might observe that in this particular case, 1/8 of the time, the secret is revealed. Now, this is for leakage estimation, but then the title of this talk promises black box leakage estimation. So what does it mean and why do we need that? Well, by black box estimation, it means that we assume we have no knowledge of the internals of our system or channel. And we still would like to carry out this leakage analysis. We still would like to understand what is the information leakage of this particular program, say. Why would we shoot ourselves in the foot? Say we are the system designers and we have built this computer program or this system more generally. Why would we consider it as a black box? Well, the reason is that often it is very hard to do to perform an analysis, a formal analysis of all the internals of the system. And this is particularly harder in the example of computer programs if your program depends, for example, has several external dependencies, for example. Now, the big advantage of doing black box leakage estimation is exactly the fact that we can tackle arbitrarily complex systems, potentially. Of course, a disadvantage is that we'll be bound to empirical measurements of the leakage, and we will never get exact mathematical expressions. And that's why in this talk, we'll be interested in doing all these empirical measurements and to back them up with some formal guarantees. Right, so as a sort of outline or roadmap of what you're going to see in this talk. So I hope I have motivated the problem of why we need black box leakage estimation. I'm going to try and be a bit more formal about the setup of the problem we consider. And I'm going to define what kind of metric do we use to estimate the leakage, be it Shannon entropy or something different. Then I'm going to try and make all things a bit more concrete and give you some attack examples. And finally, we'll move to the turning point, as I called it, of this talk, which is the equivalence of this problem with, or a correspondence with the problem of supervised learning. And finally, we will try and be a little bit more ambitious, and we'll try to think, okay, so if we had to develop a general theory for black box leakage estimation, what are the things that we can do? What are the things that we cannot do? And overall, what are the open questions in the field? So here's kind of the setup. This sort of generalizes the idea I gave you early on of analyzing a simple computer program. So the idea is that we model our system as a channel, and this channel takes as input some secret value, which is whatever we're trying to protect, and it returns some output accordingly. And to make things as general as we can, the output can be chosen according to the secret, either probabilistically or deterministically. So I'll give you some examples of attacks that can be modeled in this way. But in the example of the computer program, the secret input was, of course, the input to the program, and the output was whatever the function was returning. Now, there is just one assumption that we have to make about our channel, and that is that the channel shouldn't change over time. Formally, the channel should be stateless. In practice, this means that if we are analyzing a computer program or a machine learning model, its behavior shouldn't change over time. And well, given this setup, our goal is to determine what is the probability that some optimal attacker will be able to guess correctly this secret information from whatever he can observe. And in other words, this means quantifying the information leakage of the channel or of the output given the secret. Now, the first question I think we should answer is, well, what are we actually going to measure? So what metric are we using to quantify this information leakage? And perhaps any computer scientist would immediately reply something like, oh, perhaps we should use something related to Shannon entropy, for example, mutual information. Now, mutual information is what it measures is exactly intuitively is exactly what we want, right? So it tells us how much information is contained in the output of our black box system with respect to regarding the secret input. Well, as it turns out, mutual information and Shannon entropy in general are actually discouraged for the purpose of security or privacy, and this was an observation made by Geoffrey Smith. I believe this is one of those kind of results which are super important, but perhaps are not very mainstream yet in the community. And he said that some channel, if we were to measure a leakage by using mutual information, well, we could have even if mutual information was indicated that the channel was super secure, the attacker could still have a very significant probability of guessing correctly the secret given the output. And this is the reason why he suggested looking at what we call base vulnerability. Base vulnerability is perhaps an even more natural metric to think of a posteriori. And it measures for the optimal attacker, what is the probability that this attacker will correctly guess the secret given whatever output is given. I should also remark that in practice, we won't use directly base vulnerability, but we can use some metrics which are derived from there. Please do ask if you're interested, of course, about this, but it's not really the core of this talk. So our goal will be to measure the base vulnerability, the probability of this optimal attacker succeeding. Of course, I cannot talk about this without mentioning differential privacy. Differential privacy is, of course, a great way of quantifying or of a great metric for the leakage of a channel. It does come with a few issues, with some issues which some of you will be aware of. It is very strict, so it does impact utility in practice. But I'm going to try and not go into that discussion. One disadvantage it has is that it is very hard to estimate. So if I give you some black box system which claims to be differentially private, it is actually very hard to quantify and to assert that it is indeed differentially private. I should also note that from the target of our discussion, which is estimating base vulnerability, we can also derive some relaxations of differential privacy. One thing, please do feel free to interrupt. It's it's a Zoom discussion. I'm really happy to take questions throughout the talk. So yeah, feel free to buzz. So I'm gonna give you some examples which hopefully will concretize better the kind of framework that we're interested in. And the first example is within the data release problem. It's a problem in location privacy. So say that a certain user is willing to share their location, their GPS coordinates, but not exactly their true location, but just some noisy version of it because privacy. Now, the way we would model this in leakage estimation is as follows. We have this channel, which is whatever is adding noise to the location. On the left, you have the secret information that we're trying to protect. And on the right hand, you have the output. So say this is just a noisy version of that location. And the goal of the attacker is, given this noisy version, to guess correctly the secret location. So this is the first example. Now I'm going to move to two perhaps more compelling, although a bit harder examples. One of them is membership inference. Membership inference attacks work as follow. Suppose you have trained a machine learning classifier on some private data, and that your classifier really accepts queries. So say you can query it with pictures of penguins, and it returns some classification. Not only it returns that, it also says I'm confident, and it expresses some confidence level about its prediction. So say I'm 89% confident that this is a painter penguin. Now, what is the problem and what is the attack? Well, Chokri et al. Showed that the following is possible. An attacker with access to one of these pictures can figure out whether this picture was used for training the data of the model or not. And how can he do that? Well, I'm just going to give a very simple explanation of this, a very, if you wish, a very simplified explanation of this. If the machine learning model was poorly trained, so say it was overfitting, then it is likely that it will tend to be overly confident when making predictions about objects or pictures that it has already seen in the training process. And that's exactly why the attack may work. So how can we frame this in the framework I showed you? Well, the idea is as follows. So we know we need some secret information that we're trying to protect. In this case, it's the binary, is the answer to the binary question, is this a member or a non-member? And then we have this sort of channel, this big channel this time, which does the following. If the input is member, then it samples some picture from the private training dataset. Otherwise, if it says non-member, then it samples this object from somewhere else. And then, again, the channel or the system queries the classifier with the sampled object, and it returns as outputs that is observable to the attacker the confidence level associated with that prediction. So once again, this is pretty clear that the task also in membership inference is, for an attacker, is to guess the membership member or non-member given what is given the confidence level as output. I'm going to give a third and last example of how this framework can be used, and this is related to problems in privacy, problems in synthetic data. Now, the idea of synthetic data is as follows. We are given some data set D, and our goal is to, well, we use some mechanism to generate an artificial or synthetic data set. And this data set should, at the same time, preserve some statistical properties of the original data set, for example, the correlations. But it should also, ideally, we would also like it to be private. Now, in this definition, now for it to be private, we have to define what are our privacy requirements. And I'm going to use the requirements set by the paper you see down by Stadler, Bristena also, and Carmela Troncoso. So these data sets, these synthetic data should prevent the following two attacks. In the first attack, which is a rare identification via linkage, we give the attacker some auxiliary record, and their goal is to determine whether this record was present in the original data or not. And this, of course, just by using the synthetic data. Now, the second privacy concern, if you wish, is called attribute inference. So in this case, we give the attacker a partial record, and their goal, again, just using the synthetic data, is to reconstruct whatever is missing from this record. Now, in the interest of time, I'm just going to focus on the latter. So how do we model attribute inference attacks against synthetic data within our leakage estimation framework? Well, again, it's pretty simple. We first need to define what is observable by the attacker. In this case, it's the synthetic data and the partially completed or the incomplete data record. And the secret is whatever the attacker is trying to guess. So in this particular case, it's the value of that missing field. So does the particular patient have cancer or not? And again, the problem is phrased very, very simply, is the goal for the attacker is, again, to guess this secret given the observation. So these were three examples on how we can model real-world attacks within this framework. And this is without any modification from what researchers have been doing so far. So this is a good time for me to take questions, if there's any, on what I've spoken so far about. Cool. Either all clear or I've confused everyone. Right, hopefully not. So hopefully these attacks kind of justify the applicability of leakage estimation. So let's actually think about how we can carry out this leakage estimation. So by assumption, we can only see our system as a black box, and therefore the only thing we can do is we can query we can query the system, so we can feed it in some secrets and observe back the respective observations. And from that, our goal is to estimate this leakage, or as we said, to estimate the probability that the attacker will guess correctly the secret given the output, the base vulnerability. But of course, we would like to do so but by making a small number of queries to the system. And that's because querying the system can be expensive, depending on cases. So perhaps the simplest way to look at this problem and to solve this problem is the following. We are able to make all these Oracle queries to our black box system. And so we query it with many secrets, and we learn the respective outputs. And from this sort of data sets, if we want to call it in that way, we can count how many times each secret appears with each observation. After doing that, it's very simple that we can, by doing that, it's very simple to see that we are essentially estimating the underlying probability distribution of the channel. And ultimately, we are able to calculate the vulnerability, and that is the probability for the optimal attacker to guess correctly the secret. Now, there are several problems with this approach, and I mean the main problem is that it doesn't scale. If the input space, so if the secret space or the output space are very big, say the secret is just a few bytes of size, then it is not realistic to go through all the possible combinations and wait until all the possible combinations happen. And particularly so, of course, if secrets or observables are continuous. For example, in the case of location privacy, where the input is a continuous vector and the output is a continuous vector, we can't really use this approach without making some approximations. And this is really where machine learning comes in place. So I'm going to give you a mini primer of supervised learning, or machine learning classification more specifically in this case. And I'll show you how this almost immediately compares, or how we can immediately compare it or equate it to leakage estimation. So in machine learning classification, the first thing we have to do is select a risk notion, and that is what is the price we're willing to pay for making some mistake. So if, for example, in our case, we'll select the so-called 0-1 risk, meaning that we count one error if the classifier makes a mistake, 0 error otherwise. And we're given a data set of objects and respective labels. So the object could be pictures, and the labels could be I don't know, images. Is this an image of an alpaca or a penguin, for example? And our goal is to find the classifier or the function which achieves the smallest probability of error. And that is the classifier which guesses the correct label most often, if you want. Now, this ideal classifier is called the Bayes classifier, and the corresponding error is the Bayes risk. Now, what are we trying to do with leakage estimation, and particularly in our framework? Well, again, we have defined a sort of risk for the attacker, and our goal is again to find the attacker which is the most likely to guess a secret given some output of our channel. But then it is almost trivial, I think, to observe that the two fields are trying to solve a very, very similar problem. One is looking for the minimizer of the risk, the other one for the maximizer of the vulnerability. But these two quantities are simply very trivially the complement of the other. So this trivial fact can actually be used and does have very, very interesting practical repercussions. Well, first of all, an observation. In the reason why machine learning is so effective when carrying out the attacks that I've showed before. So, for example, against synthetic data rather than membership inference, is exactly this equivalence. In both cases, we are trying to solve the same problem, and a machine learning classifier is also trying to be our optimal attacker. Now, much more interesting, I think, is that there are many tools from learning theory which we can use for quantifying the leakage. So I'm going to show you two examples of these tools in the next couple of slides. The first example starts with the nearest neighbor classifier, which is perhaps the simplest classifier you can think of. The idea of nearest neighbor is that you're given some data sets of labeled objects, and you're asked to predict the label for some unseen object. Now, the nearest neighbor classifier tells you just output the label of the closest observation to this. Now, why am I speaking about nearest neighbor? Well, a very, very beautiful paper by Coover and Hart from '67 showed that there is a relation between the base risk, and that is this R star, which is the smallest risk achievable by any machine learning classifier, and the risk of the nearest neighbor classifier. And let me just remark, because of the equivalence between leakage estimation and supervised learning, the base risk is just a complement of the vulnerability. So in other words, we just found a bound on the vulnerability, which is the quantity that we wanted to estimate. So, so the idea is as follows. We can do it in practice. We have our channel, and we query it with our choices of secrets, get back respective observations, and we create this sort of data set. And on the basis of that data set, we can estimate the risk of the nearest neighbor classifier. And from that, we get, in this case, an upper bound on the vulnerability. We discover that the channel is at most this vulnerable to a particular attack. But then we may want to be even a bit more ambitious and say, okay, can we actually estimate the vulnerability directly? Well, we can just use the K nearest neighbor classifier in this case. This was, again, a very nice paper, in this case by Stone. And it showed that by using the K nearest neighbor classifier, and this time the classifier just takes a majority vote over the labels of the K closest observations. If we select the K parameter in a certain way for K and N, then its expected risk will converge to the base risk, and therefore we have a direct estimate of the vulnerability of the channel just by using K nearest neighbor. Now, I showed you two cases, in this case, two methods which we can use from the machine learning literature. As it turns out, there's an entire class of methods which have the same behavior of the K nearest neighbor classifier. So under particular conditions, for example, subtor vector machines can also be used in a similar way to estimate the base risk and therefore to estimate the leakage of a channel. So this gives us plenty of options to play with. Now, These are some results I have when for applying machine learning methods for quantifying the leakage. In this particular case, on the system was adding some noise. So on the left-hand side, you see this sort of the noise added, for example, when the secret value was 5,000, and therefore the respective observations or output of the channels would be sampled according to this distribution. And similarly for the adjacent secrets, this would be the distribution. And the results quantify our performances in terms of how many queries we have to make to our channel in order for our estimate to converge. And I mean, the observation is very simple. The ones at the top at the bottom are all universally consistent rules. These are so K and N, nearest neighbor, and so on. Whilst this one you see is this one in pink is the frequencies approach, which is kind of what was the de facto standard before our methods. Right. So one particular remark is that so far, and all the methods we have seen so far, considered secret values which came from a finite set. For example, for membership inference, the secret value takes binary value, and so on. But of course, there are cases where the secret that the attacker is trying to guess is continuous. For example, in location privacy, where the attacker is trying to guess the GPS coordinates. And well, as it turns out, we can again use machine learning to carry out this analysis. It is actually pretty straightforward once we have done the observation. This time, of course, we have to define a different risk function. So, for example, the attacker is evaluated in terms of his prediction with respect to the L1 distance or L2 distance from the secret. And again, we can use, for example, KNN regressor in this case to carry out this analysis. Right. So we have a tool. We are maintaining a tool for carrying out this leakage estimation. Now, I think if there's just one takeaway from all of this, is that if you have an attack, if you're carrying out an attack by using machine learning, then it's very, very likely and very simple, probably, to run F-BLEAU to get a leakage, a notion of leakage for the system you're trying to evaluate or the attack setting you're trying to evaluate, and of course getting security guarantees. Now, as I said at the beginning, we're going to try and be a little bit more ambitious and think of what are the things that we need to care about if we wanted to establish a general theory of leakage estimation. And of course, a theory is defined by the things that we cannot do. So I'm going to show you two impossibility results for leakage estimation. And I have to say, once again, these impossibility results come directly from the machine learning literature. And it was just a matter. And of course, they came consequently into leakage estimation after we made this observation. So the first question one may have is that, well, we have all these nice tools which enable us to estimate the leakage of our channel given a certain number of queries. Now, the natural question is, well, how many queries do we need? Or what is there any convergence rate that we can prove, saying that will do delta better as the number of queries increases. And well, Antos et al. Proved that this is not possible. And in particularly, if the output space, so whatever is measurable by the attacker, is continuous, then we cannot prove any convergence rate. What it means is that there exists some channels for which our leakage estimator would infinitely fail to converge, essentially. And something very interesting is that this doesn't hold just for machine learning based estimators. It holds for all base risk estimators, or equivalently vulnerability estimators. Now, another question you may have is, okay, can we at least say that one estimator is usually better than another one? And well, a famous result called no free lunch theorem by Woodpert answers negatively also this question. For any two estimators, and in our context, for any two leakage estimators, there's exactly as many systems or channels such that the first one is better than the second one and the other way around. So the takeaway from this is, again, we should just try as many estimators as we can. And the good news, of course, is that machine learning learning theory gives us several estimators, an entire class of these universally consistent estimators which we can use. Now, just as a kind of bonus slide, this is a program which makes our nearest neighbor and k nearest neighbor estimators fail miserably bad, and this is of course in line with the no free lunch theorem that we saw in the previous slide. So this program works as follows. It takes as input two values for the secret, 0 or 1. If the secret is 0, then it returns an even integer. Otherwise, it returns an odd integer. Now, the nearest neighbor idea is based on the fact, or on the intuition, that similar observations and neighboring observations should have the same label or secret. And in this case, we're making exactly the opposite. And on the right-hand side, you see how badly these leakage estimator fail. Now, luckily for us, these kind of systems are actually quite rare in practice. Usually, we are the designers of a system, and therefore we can prevent these sort of things. But of course, there is the possibility, and this is something we have to keep thinking about. I wanted to spend some final 3-4 minutes on open questions. I think if there is one thing I would like to have as outcome of this talk, is mostly to get you excited to work on some of these problems. And well, the first open question, it's phrased in a sort of ridiculous manner, I think. Solving supervised learning means solving black box leakage estimation. The two fields are going hand to hand, and improvements for one will lead to improvements for the other one. And therefore, there are very interesting directions in machine learning on small sample convergence. So how well can we do with a finite number of queries? And well, all of these ideas, I think, are worth exploring. And the reason is that by solving and by improving machine learning, we'll also be able to improve leakage estimation. Of course, it isn't enough to improve machine learning practically. In the context of security, we do need guarantees, and that's really what we seek for. A second open question, and perhaps it will come natural when after I mention the black box assumption, is, well, can we use somehow machine learning together with internal knowledge of our system or say computer program? Can we use this knowledge together to get better performances, better guarantees? I think this is very much possible, and it's definitely a nice thing to start looking at. There is one very nice feature that previous work on leakage estimation had, and that is the possibility of doing a leakage or no leakage test. Sometimes you have a system and you only care about whether it leaks information or it doesn't. You don't care about measuring how much it leaks. So it would be interesting to see whether we can use machine learning to carry out this sort of leakage. Another question, another open question, I think, and very much open question is, can we model active attacks by using by extending our framework and by using this sort of machine learning guided analysis? All the attacks you have seen are passive attacks, and where the attacker cannot interact with the channel in order to guess better the secret. And active attacks would be a very interesting area to explore in this sense. And finally, there are several extensions that we can think of. It is possible to extend our ideas to settings where the attacker sees more than one outputs of the channel instead of just one, and also cases where the attacker is interested in, for example, guessing just part of the secret and not the entirety of the secret. So I'm going to conclude with this very busy slide. Apologies for this. Leakage estimation, hopefully I convinced you, is applicable to several attacks. We have seen side channels, synthetic data, and membership inference are very much possible to study within this framework. And luckily, the machine learning theory can help us a lot in solving this kind of black box estimation problems. We've also discussed what kind of open challenges there are in the context of leakage estimation, and I'm just going to leave you with two takeaways from this talk, and that is that with leakage estimation guided via machine learning in the way I presented it so far, what it gives us really is some guarantees on our estimates, and that's really what we're interested in security. And that ideally, and if you already have a machine learning based attack, then you can probably use these techniques directly to quantify the leakage. So I'll be happy to take questions. I can see 7 minutes remaining. So yeah, please shoot.
Yeah, thanks a lot, Giovanni, for this very nice talk. Yeah, does anybody have any questions? Now is the time. So I have a question. You were presenting these impossibility results, right? And in particular, like going back to this first one that you showed, this about, what was it, like continuous convergence impossibility. Is there, if you have a channel that has some continuous output, is it possible to like use some of these results to better protect your channel against leakage? I mean, sorry, I'm no expert. If this question does not make any sense, but
Yeah, it's actually a super interesting question. It's first of a kind. I mean, the idea is that, okay, the one issue, I was thinking, yeah, in theory, it should be possible, right? So your idea is, I have the channel, I'm the builder, designer of this channel. And
yeah, exactly.
I know that if I design the channel weirdly, I output things in a particular way, then I will confuse the attacker.
Yeah,
I
exactly.
think this is a great observation. One issue I see is the following. So this is of course a very informal version of the theorem, but what the theorem says is that for any estimator, okay, there exists a particular channel or a particularly malicious distribution for which that estimator will fail to converge. So in another way, if you design your channel to be super weird, it may work against some attacker or some estimator, but not against all of them.
Yeah, right. So the usual problem that you have as a defender, right?
Yeah. But it is an interesting question, because many machine learning models, which are usually what is being used, to carry out this sort of attacks, they tend to react similarly to similar patterns. So if you somehow, they all behave similarly, and I would expect they would all behave similarly with similar with your particularly malicious channel. So yeah, it could be possible. Yeah.
Okay, thanks. So there is one question on the chat. Would be an example of an estimator that would solve the Spiky case, question mark.
That's a very, very good question. Okay, my first answer is that if you look at the frequentist approach, the frequentist isn't doing too poorly. It is frequentist that is just, counting how many times it sees some observation and the corresponding secret. There is a very overfitting estimator, which is the estimator that when the output number is even, guesses immediately 0. When the output is odd, it always outputs 1. So that particular estimator, it's not really a trained estimator, right? But it gives you an example that this channel is perfectly solvable. Yeah, exactly. It's the perfect estimator for that particular case. It would probably be, very bad in any other case. But I think the main answer I would give you is, in that case, I would use the frequentist estimator. Yeah. Okay.
All right. So another question, systems questions, is I see F-BLEAU is written in Rust. Can you comment on your experience using Rust for this?
Yes, absolutely. Rust is an amazing language. Okay, so I started using it a few years ago. And as a researcher, I try to use it for projects which are kind of in a final stage. So if I have to explore with ideas, I would just use Python. But for production level codes, I try to use Rust. Why? Efficiency is for sure one reason. It's comparable to C++, and F-BLEAU is doing a lot of internal computations, and it's quite it'd be quite heavy to do on Python. A second reason is maintainability. After a year, I hadn't been looking at Rust. I was at my particular code, I was able to jump in, make some modification, and the type system helped me a lot to fix everything. If I had done that in Python, I probably, it would have taken me much, much longer. So yeah, Rust takes longer to, well, to learn, of course, but also like to write your actual software. But then maintenance, I think, is a big plus. Yeah.
Nice. So what does F-BLEAU stand for?
Oh, well, that's also a fun question. Well, F-BLEAU stands for, I can't remember what the actual acronym stands for. It's like Fast Black Box Leakage Estimation. Of course, I mean, the actual purpose of F-BLEAU is that Fontainebleau is an amazing forest in near Paris where there's loads of climbing, and with some of my collaborators, we were like, our goal was to go climbing. We ended up, doing research. So
nice.
that is the reason of F-BLEAU. Yeah.
Okay. Cool.
Yeah.
So any further questions? I think we can take another short one.
Yeah, I'm happy to. I mean, Zoom experience of giving presentations. So hopefully next time we'll do a proper one at UCL. Well, a proper one, a physical one at UCL.
Right. Yeah, definitely.
It's weird. It's really changing our habits.
Yeah.
Right. Yeah.
Okay. Yeah, I think there are no further questions.
If you have more questions, somehow you should be able, you know how to reach me. So yeah.
Yeah. Thanks a lot, Giovanni. It was really great for having you.
Thank you, Giovanni.
Yeah.
You had someone who really listened carefully.
Yeah, I can see it. Does she have any questions?
Like she wants to ask, why do you guys waste your time doing PhDs and working in academia when you can make much more money and buy me more toys?
Exactly.
Yeah,
that's the question.
That's a very good, very good question. And not sure how to answer to that. We might have to take it offline.
Okay. Ciao, ciao, Maria. Ciao, ciao. Ciao, ciao. Okay. Thank you, Giovanni.
Okay.
Very good talk. I really enjoyed it.
Thank you, guys.
Thanks a lot, everyone.
Thank you.
And make sure to come back for the next session in 2 weeks. Okay. Take care. Bye.